On the night of August 24th, 1989, in a quiet building in Pasadena, California, a few hundred people sat watching a wall of screens. Some of them had been waiting for this night for 12 years. Some had been waiting their entire careers. Think about how long 12 years is. When this machine left Earth, in the summer of 1977, disco was on the radio, and the first Star Wars film was new in theaters. The engineers who launched it had slide rules on their desks. By the time it reached its final destination, the Berlin Wall had 3 months left to stand. Children who were born the week of launch were finishing school. And through all of it, every day, every night, through the entire decade in between, the machine simply fell, outward, through the dark, toward an appointment that had been calculated before some of the people now monitoring it had even joined the mission. 400 million kilometers away, 2.7 billion miles. That machine, the size of a small car, was now falling toward the top of a blue planet. It carried cameras built in the early 1970s, a transmitter about as powerful as a refrigerator light bulb, and the hopes of everyone in that room. The machine was called Voyager 2. The planet was Neptune. And here is the detail I have never been able to let go of. The radio signals from that encounter took 4 hours and 6 minutes to reach the Earth. So when the first pictures began to appear on those screens in Pasadena, everything they showed had already happened. The flyby was already over. The spacecraft had already survived. Or it had not. The people in that room were not watching an event. They were watching the light of an event, arriving late, like the glow of a lamp switched off 4 hours ago. I find that image stays with me, because in a very real sense, that is the only kind of seeing we have ever done at Neptune. One machine, one pass, one long night of data delivered after the fact, and then silence, stretching from that August evening all the way to tonight. This is not really a story about a spacecraft. There are many stories about Voyager 2, and some of them are wonderful. But tonight, the spacecraft is only the messenger. This is the story of the world it met, the last true planet. A place so far from the sun that noon looks like deep twilight, so far that it has completed only one full orbit since human beings first learned it existed. A place that should, by every reasonable expectation, be still and frozen and dead, and is instead home to the fastest winds ever measured on any world we know. Tonight, we are going to travel there slowly, the way the machine did. And if you are here to fall asleep somewhere along the way, that is not a failure of the journey. That is what this channel is for. The story will go on without you, gently, and Neptune will still be there tomorrow. If you find these long journeys worth keeping, a like or a subscription quietly helps more than you might think. That is the only time I will ask. Now. Before the storms, before the stolen moon, before the diamond rain, I want you to understand just how far away we are going. Every map of the solar system you have ever seen has lied to you a little. It has to. If the pages were honest about the distances, the book would be the size of a city. So let me try honesty instead. Imagine the sun shrunk to the size of a grapefruit, sitting on a table in the middle of a large park. On that scale, the Earth is a grain of sand about 11 meters away, 36 feet. You could walk it in a few seconds. Jupiter, the giant of our neighborhood, is a small marble 57 meters from the grapefruit. Saturn, about 100 meters, the length of a football field. Even mighty Saturn, with its rings and its dozens of moons, lives only a football field from the table. Uranus is 2 football fields away. And Neptune is a grain of rice 330 meters from the grapefruit. A 5-minute walk across the whole park, past everything else the sun owns, out to where the grass ends and the streetlights begin. 30 times farther from the sun than the Earth. 4.5 billion kilometers. Light itself, the fastest thing there is, leaves the sun, and travels for more than 4 hours before it arrives there, tired and thin. And when it arrives, there is so little of it left. For every 900 units of sunlight that fall on your face at noon on Earth, Neptune receives 1/900th. Noon on Neptune is about as bright as the last few minutes after sunset here, that deep blue hour when the streetlights come on and the world softens at the edges. That is the brightest it ever gets. And the sun itself, seen from Neptune, is no longer the sun you know. It does not look like a disk anymore. It looks like a star, the brightest star anyone has ever seen. A brilliant, hard point of light, 30 times smaller across than the sun in our sky. You could cover it with a pinhead held at arm's length. All the warmth of the entire solar system compressed to a spark. The cold runs just as deep. At the cloud tops, the temperature sits near minus 218 degrees Celsius, minus 360 Fahrenheit. Only a few dozen degrees above absolute zero, the temperature at which atoms themselves grow still. Numbers like that slide off the mind, so let me put it another way. The coldest temperature ever recorded on Earth, the coldest moment in the coldest winter at the most hostile research station in Antarctica, was about minus 89 degrees Celsius. Neptune's everyday weather is 130 degrees colder than the worst place on our planet has ever been. On Neptune, the air of an Antarctic winter would arrive as a heat wave. Everything we know about weather says that a place like that should be quiet. Weather is an engine, and engines need fuel. Sunlight stirs the air, lifts the water, drives the winds. Starve a world of light and you should get stillness, a frozen, changeless calm. Neptune has heard this argument, and Neptune is not interested. Because on this dim, frozen rice grain at the edge of the park, the wind blows at more than 2,000 kilometers per hour. 1,200 miles an hour and more, faster than the speed of sound on Earth, faster than any hurricane, any tornado, any gust ever recorded on any other planet, including Jupiter, which sits 25 times closer to the fire. The coldest giant, the dimmest sky, the fastest wind. That contradiction has been sitting in our textbooks for 37 years now, and I will be honest with you from the start, the way I always try to be. We still cannot fully explain it. There is more. This planet radiates more than twice as much energy as it receives from the sun, warmth rising up from somewhere inside that no one has ever seen. Its magnetic field is tilted and lopsided in a way that would make a compass useless, and which hints at oceans of a kind of water that exists nowhere on Earth. It may rain diamonds there. Not as a poetic image, as a serious hypothesis, tested in laboratories with lasers. Its largest moon circles it backwards, the only large moon in the solar system that does. Because, as we will see, Neptune almost certainly stole it. Stole it from the same family of small, cold worlds that Pluto belongs to. And that theft, some scientists now suspect, may have knocked the entire planet sideways. And around all of it, thin rings of dust hang in incomplete arcs that should not be able to exist, named Exelden. I have always loved this feature: liberty, equality, and fraternity. One visitor, one night. Everything I have just told you either comes from those few hours in August 1989, or from astronomers straining to see, across 4.5 billion kilometers, a world smaller in their telescopes than a coin seen from across a stadium. It is worth pausing on how strange that is. Jupiter has been visited by 9 spacecraft. One of them circled it for years, and another is circling it now. Saturn had a machine in orbit for 13 years, weaving between its moons. Even Pluto, smaller than our own moon, demoted from planethood, 85 years between its discovery and its close-up. Even Pluto has had its portrait taken from nearby. Neptune, a world 17 times the mass of the Earth, a full-grown giant planet with rings and 16 moons and the wildest weather in the sun's whole family, has had a single guest, for a single day, 1 generation ago. Every close-up photograph of Neptune that exists, every single one, in every textbook and every documentary, including many of the images accompanying my voice right now, was taken during that one encounter, by one machine, in the last week of August, 1989. That is the journey ahead of us tonight. It unfolds the way the story itself unfolded. First, a planet that was discovered before it was ever seen, found not with a telescope, but with a pen, in one of the strangest detective stories in the history of science. Then, a 12-year voyage, and the single night that taught us almost everything we know. Then the world itself, the impossible winds, the storms that appear and vanish like thoughts, the interior where the diamond rain falls, the stolen moon with its ice volcanoes quietly spiraling toward its own destruction, the rings, the resonances, the strange kingdom Neptune rules at the edge of the map, including its long, patient dance with Pluto. And at the end, the question that has no comfortable answer: why no one has ever gone back, and what it will take for anyone to see that blue light up close again. So make yourself comfortable. Let your shoulders down. Let the day you just had grow small behind you, the way the sun grows small behind an outbound spacecraft. Still there, still warm, just no longer the loudest thing in the sky. The park is dark, the grapefruit sun is far behind us, and we are walking out toward the rice grain at the edge of the grass. There is no hurry. Nothing in this story moves quickly except the wind, and the wind will wait for us. Neptune has been patient for 4.5 billion years. It can be patient for one more night. We begin more than a century before that night in Pasadena, in an observatory in Berlin, on the evening of September 23rd, 1846, where a young astronomer is about to open a letter from Paris. The letter asks him to look for something that, as far as the entire human race knows, does not exist. He will find it before midnight. Every planet humanity had ever known was found the same way. Somebody looked up. Mercury, Venus, Mars, Jupiter, Saturn, nobody discovered them at all. They are bright, they wander among the stars, and people in every culture on Earth have watched them since before writing existed. Then, in 1781, a musician changed everything. William Herschel, a German-born organist living in England, building telescopes in his spare time, pointed one of them at the sky and noticed a small disk that did not belong. He thought at first it was a comet. It was not. It was a new planet, Uranus, and with it, the solar system doubled in size overnight. For our story, what matters is not Uranus itself. What matters is what Uranus did next. It misbehaved. Astronomers of that era were very good at one particular thing: predicting where objects in the sky ought to be. Newton had given them the law of gravity, and the mathematics that flowed from it was, by the early 1800s, exquisitely precise. You could compute a planet's path decades into the future and expect the sky to obey. Uranus refused. Year after year, decade after decade, it drifted away from its predicted position. Not by much. The error would have been invisible to the naked eye, if the naked eye could see Uranus at all. But to the astronomers charting it, the discrepancy was glaring, and it would not go away. By the 1830s and 40s, the mystery had hardened into a genuine crisis. Something was pulling on Uranus. Either Newton's law of gravity, the foundation stone of all physical science, quietly broke down at great distances, or there was something out there. Something massive, unseen, tugging at Uranus from the darkness beyond. I want you to appreciate what happened next, because I think it is one of the most audacious acts in the history of human thought. In Paris, a mathematician named Urbain Le Verrier sat down at a desk with paper and ink and set out to compute the invisible. Given how Uranus was being pulled from this direction in this decade, from that direction in another, he would work backward to the puller, its mass, its orbit, its position in the sky today. The calculation was monstrous. No computers, no calculators. every step by hand, thousands upon thousands of steps, month after month. He was, in effect, performing the detective work of the century with the only instruments he trusted: arithmetic and Newton's law. In the summer of 1846, Leverrier finished. He announced a position. The unknown planet should currently stand in the constellation Aquarius, at a spot he specified to the degree. And then something almost comic happened. Nobody in France looked. The observatories were busy, or skeptical, or slow. Leverrier, out of patience, wrote a letter to a young astronomer in Berlin named Johann Gottfried Galle, essentially begging him, "Point your telescope here." The letter arrived on September 23, 1846. That same night, that very night, Galle and a student assistant named Heinrich d'Arrest opened the dome of the Berlin Observatory. Galle called out star positions from the eyepiece. d'Arrest checked them, one by one, against a freshly printed star chart. Within an hour, Galle read out an 8th magnitude point of light. d'Arrest scanned the chart and then said the words every astronomer dreams of hearing. That star is not on the map. It stood barely 1 degree from where Leverrier's arithmetic said it would be. 2 moon widths. After a calculation reaching across 4 billion kilometers of space, the pen had missed by 2 moon widths. They watched it the next night. It had moved, exactly as a distant planet should. There was no doubt left. For the first time in history, a world had been discovered not by looking, but by thinking. The French physicist François Arago found the perfect phrase for it. Leverrier, he said, had discovered a planet with the point of his pen. The new world needed a name. Leverrier proposed Neptune, god of the sea, and then, flush with glory, tried quietly to have it renamed after himself. The rest of the world's astronomers politely ignored that. Neptune it was, and Neptune it stayed. The deep blue planet named, before anyone knew its color, for the deep. Now, the story is actually messier than the legend, and the mess is worth 2 minutes of our night because it is very human. Across the channel, a young Cambridge mathematician named John Couch Adams had been wrestling with the same problem, on and off, for years, and had arrived at broadly similar answers. He had tried to get English astronomers to search. Through a chain of misunderstandings, unanswered letters, and a certain amount of institutional fog, the search in England was slow, half-hearted, and unlucky. In August 1846, weeks before the Berlin night, the English survey actually recorded Neptune twice, and failed to notice because their charts were not up to date. When the discovery was announced from Berlin, a bitter priority fight erupted, French newspapers accusing the English of trying to steal the glory, English institutions scrambling to establish Adams's claim. For a century and a half, textbooks split the difference and called Adams and Leverrier co-predictors. Modern historians, who have dug through the original papers, including a crucial file that went mysteriously missing from an English observatory for decades, tend to give the lion's share of the credit back to Leverrier. Adams's calculations were real, but they wandered. Leverrier's were public, precise, and they pointed like a finger. However you assign the glory, one fact is untouched. The planet was found because 2 people, independently, trusted mathematics enough to tell telescopes where to look. There is a coda to Leverrier's triumph that I think makes him more, not less, admirable, because it shows how hard this game really is. Years later, he tried the same trick again. The planet Mercury also drifts from its predicted path, ever so slightly. And Leverrier, reasoning exactly as before, computed an unseen planet inside Mercury's orbit, scorched against the sun. He named it Vulcan. Astronomers hunted it for decades. It does not exist. Mercury's drift was real, but the explanation was stranger than any hidden world. It took Albert Einstein, in 1915, to show that Mercury wobbles because space and time themselves curve near the sun's mass. The same evidence, the same brilliant method. One time it finds a planet, The other time it finds a crack in Newton's universe. The pen is mighty, but the universe writes back. And here is a twist I have always loved. Once astronomers knew where Neptune was, they went back through old records to see if anyone had ever seen it without knowing. Many had. It had been logged as an anonymous star at least a dozen times. The most remarkable name on that list is Galileo Galilei. In the winter of 1612 to 1613, 234 years early, Galileo was observing Jupiter and its new moons through his little telescope, and in the margin of his notebook, he plotted a faint star nearby. That star was Neptune. On a later night, he even noted, with a hint of puzzlement, that this particular star seemed to have shifted relative to another. It had. It was a planet, sliding slowly along its orbit, whispering to the greatest observer alive, and the whisper was just below the threshold of hearing. His telescope was too small, the motion too slow. He moved on. I do not tell that story as a tragedy. I tell it because it says something lovely about discovery. The universe does not hide from us so much as wait for us. Neptune shone in Galileo's eyepiece, patient, unrecognized, for centuries. It could afford to wait. It moves on a schedule unlike anything human. Because Neptune is so far from the Sun, its year, one full circle of its orbit, lasts 165 Earth years. Let that stretch out for a moment. Not a lifetime, 2 lifetimes, laid end to end. Since the night Galilei and d'Arrest found it, Neptune has completed exactly 1 orbit. 1. The anniversary fell on July 12, 2011. 165 years after the Berlin night, the planet returned to the place among the stars where humanity first caught it. Everything we have ever done, every war and vaccine and moon landing, every photograph, every radio broadcast, every human being who has lived and died since 1846, fits inside a single Neptunian year. Its second year of being known will not end until the 22nd century, in 2176. A world where a year outlasts nations, where the seasons, and it does have seasons, we will come to them, each last around 40 Earth years. A child born at the start of a Neptunian winter would be a grandparent before spring. For more than a century after its discovery, that was almost all Neptune was, a schedule and a dot. Through even the largest telescopes on Earth, it showed as a tiny, blurry, blue-green bead, 2.5 arc seconds across, about the size a coin appears from 2 kilometers away. Astronomers measured its orbit, weighed it by the motion of its moons, guessed at methane in its air from the color of its light. William Lassell, an English brewer with a fine telescope, spotted its great moon Triton just 17 days after the planet itself was found. Hold that name. It owns a whole chapter of tonight's story. In 1949, a second moon, Nereid, turned up. Beyond that, the file stayed thin. Neptune was a fact, not a place. No surface anyone could map, no weather anyone could watch. A dot with a birthday. And it might have stayed that way for another century, except that in the 1960s, a graduate student doing orbital arithmetic noticed something extraordinary about the end of the 20th century. The giant planets, on their slow, separate circles, were drifting into a rare alignment. A spacecraft launched at just the right moment could ride gravity from one to the next, Jupiter to Saturn, Saturn to Uranus, Uranus to Neptune, like a stone skipping across a pond, each world bending its path and flinging it onward to the next. The alignment comes once every 176 years. The last time it had occurred, Thomas Jefferson was president, and humanity's fastest vehicle was a sailing ship. This time, we had rockets. The window would open in 1977. The dot found with a pen in 1846 was about to receive its first, and so far its only, visitor. But between the deciding and the arriving lay 12 years of flight, a crippled radio, a frozen camera platform, and a series of gambles that, looking back, still seem barely believable. That voyage is where we go next. In the summer of 1977, on a concrete pad on the coast of Florida, a rocket stood waiting in the heat. Folded inside its nose cone was a machine that weighed less than a small car, 825 kilograms, about 1,800 pounds, and looked, honestly, a little awkward. A 12-sided metal box, a white radio dish 3.7 meters across, a spindly boom holding its nuclear power source away from the instruments like a lantern held at arm's length. Its builders called it Voyager 2. It launched on August 20th, 1977, and in one of those quirks of orbital mechanics that sound like a riddle, Voyager 1 launched 16 days later. Number 1 was sent on a faster path. It would overtake its twin inside the asteroid belt and reach Jupiter first. But it is the slower sister that owns tonight's story. Because only Voyager 2 was aimed along the full length of the once-in-176 years road, Jupiter, Saturn, Uranus, Neptune. All 4 giants, one machine. I want to be honest about what this machine was, because the numbers still astonish me. Its computers could hold, altogether, about 69 kilobytes of memory. The phone charging beside your bed tonight holds roughly 1 million times more. Its onboard processors executed a few thousand instructions per second. Your phone manages tens of billions. It recorded data on an 8-track tape machine. Its radio transmitted with 23 watts, about the power of the bulb inside a refrigerator. That refrigerator bulb was expected to stay in touch across 4.5 billion kilometers. And here is the part that I find genuinely moving. Nothing about the Neptune leg was guaranteed. The mission, as officially approved and funded, ran only through Saturn. The Grand Tour in its full glory had actually been canceled years earlier as too expensive. Voyager was the budget version, formerly a Jupiter-Saturn mission. But the engineers who designed it, quietly, deliberately, built a machine capable of more, and aimed it so the road to Uranus and Neptune stayed open. They packed provisions for a journey nobody had yet paid for. So Voyager 2 swept past Jupiter in the summer of 1979, photographing its churning storms and the erupting volcanoes of the moon Io, the first active volcanoes beyond Earth, which its faster twin had discovered just months before. It threaded the Saturn system in August 1981, and the gravity of each world bent its path and flung it onward, the stones skipping across the pond. And at Saturn, things started to break. Days after the closest approach, the scan platform, the movable shoulder that aims the cameras, jammed. Seized solid mid-turn, with the encounter still underway. Pictures smeared into streaks. Targets slid out of frame. Engineers on Earth eventually coaxed it back to life and diagnosed a lubrication failure. Work the joint too hard, too fast, and it would grind itself to a halt. This time, maybe forever. Worse had already happened, years earlier, in the quiet of the cruise. In 1978, Voyager 2's primary radio receiver, its ears, failed outright. The spacecraft switched to its backup. The backup was sick too. A bad capacitor had left it nearly tone-deaf, able to hear Earth only within a razor-thin band of frequency. And that band drifted. As the receiver warmed or cooled by fractions of a degree, the frequency it could hear slid around, so controllers had to calculate, every single time, precisely what pitch to broadcast so that, after the Doppler shifts of a moving Earth and a receding spacecraft, the signal would land inside the sliver of hearing of a half-deaf radio billions of kilometers away. Sit with that arrangement for a moment. For the entire rest of the mission, every command, every software update, every course correction for 11 years, humanity's only channel to its most distant explorer was a broken backup radio that could only hear one note, and the note kept moving. And still it worked. In January 1986, 4.5 years after Saturn, the patched and hobbled spacecraft reached Uranus, the first machine ever to do so, and did its job flawlessly. It found a strangely bland, fogged-over world, a planet lying on its side, with a scarred little moon called Miranda that looked like it had been shattered and reassembled. The encounter was a triumph of engineering over entropy, but the world barely got to celebrate it. 4 days after Voyager 2's closest approach to Uranus, the Space Shuttle Challenger broke apart over Florida, and 7 astronauts died in front of a watching planet. The Uranus flyby, the only visit humanity has ever paid to that world, slid quietly off the front pages, folded into one of the darkest weeks in the history of spaceflight. I have always felt that Uranus deserved better. It never got its parade, which meant that Neptune, 3.5 years further down the road, would carry a double weight. The last new planet, and the last chance for this mission, this whole generation of explorers, to end in daylight rather than shadow. This was the machine, half-deaf, stiff-shouldered, running on 1960s memory, that was now falling toward the hardest target of the entire tour. Because Neptune was, by every measure, the worst place the mission had ever attempted. Consider what the engineers were facing. Light. At Neptune, sunlight is 900 times weaker than at Earth, 3 times dimmer than at Uranus, which had already strained the cameras. Photography in that gloom means long exposures. Long exposures from a spacecraft sweeping past at tens of thousands of kilometers per hour means smeared, ruined images. Unless the whole spacecraft turns, smoothly and precisely, to track its target while the shutter is open, like a photographer panning with a passing cyclist. The engineers taught a machine 4 billion kilometers away to do exactly that, to fire its tiny thrusters in choreographed pulses, rotating the entire craft with the gentleness of a minute hand, all timed on its own, with no human in the loop, because no human could be. A command sent at the moment of a mistake would arrive 4 hours too late. Data. A weak transmitter, an immense distance. The mathematics of radio is unforgiving, and at Neptune's range, the data would trickle at rates a modern connection would not even register. So engineers reprogrammed the spacecraft in flight to compress its own images, teaching a 1977 computer new tricks 11 years after launch, and then rebuilt the listening Earth to catch the whisper. The Deep Space Network's great 64-meter dishes in California, Spain, and Australia were enlarged to 70 meters. The Parkes radio telescope in Australia was recruited. So were all 27 antennas of the Very Large Array in New Mexico, linked together, their collected signals stitched into one. By August 1989, for a few weeks, a measurable fraction of humanity's total radio listening capacity was aimed at one small machine, straining to hear a refrigerator bulb from 4 billion kilometers away. And then there was the question of the path itself. And this choice, I think, is where the story quietly becomes beautiful. Voyager 2 could have been sent past Neptune at a polite, safe distance, taken its pictures, and sailed on. But mission planners wanted more than Neptune. They wanted Triton, the big backwards orbiting moon, the mystery Lassell had spotted 17 days after the planet's discovery, the world some scientists suspected, rightly, as it turned out, might be one of the strangest in the solar system. Orbital mechanics offered a bargain. To bend the spacecraft's path down toward Triton, Voyager 2 would have to skim Neptune close, shockingly close. The trajectory the planners chose threaded the machine over Neptune's north pole at an altitude of about 4,950 kilometers above the cloud tops, 3,000 miles. After a 12-year, 7 billion kilometer journey, the spacecraft would clear the planet by less than the length of a single flight from New York to London. It was the closest approach to any world in the entire Voyager program, closer than either spacecraft had ever dared come to anything. Close carried risks. Perhaps ring debris, invisible from Earth, orbiting exactly where the spacecraft would pass. Perhaps an upper atmosphere that reached higher than models predicted, enough to tumble the craft. The navigation itself had to be nearly perfect. Arrive a little off, at the wrong angle, and the gravitational slingshot toward Triton would miss its mark, and there would be no second pass, no orbit, no going around again. Voyager 2 was moving far too fast for Neptune to hold. One approach, one polar crossing. 5 hours later, Triton. Then the road ends. Nothing ahead but interstellar space, forever. Every previous encounter had a safety net of sorts. Another planet ahead, another chance for the mission to matter. Neptune was the last stop. The final exam taken once, at the end of a 12-year semester, by a machine that could not hear well, could not turn its camera shoulder quickly, and could not, under any circumstances, ask for help in time. Through the spring and summer of 1989, Neptune grew in Voyager's approaching cameras. First a dot, the same dot Gale had seen, the dot Galileo had sketched. Then a disk. And then, weeks out, something that made the scientists sit forward in their chairs. The dim, frozen world at the edge of the map, the planet that its own textbooks predicted should be a featureless haze, had weather. There was a storm in its southern hemisphere the size of the entire Earth, a dark, slate-blue oval staring up like an eye. There were bright silver clouds casting shadows. Something small and fast and white scooted around the planet so quickly the team simply started calling it Scooter. Day by day, frame by frame, the pictures sharpened, and the impossible became undeniable. Neptune was alive with motion. At the Jet Propulsion Laboratory in Pasadena, the corridors began to fill. Scientists who had launched this mission with dark hair returned to see it end with gray. Press from around the world set up cameras. There was a sense, people said afterward, of a graduation, a wedding, and a funeral all scheduled for the same week, the triumph of arrival, and the finality of it. Whatever those few hours revealed would have to last science for decades. Nobody imagined just how long. The night of August 24, 1989, settled over California. 4 billion kilometers away, 4 hours and 6 minutes ago, a small, worn, magnificent machine was already crossing the top of the blue planet. What it found there is the next chapter of our night. There is a photograph from the Jet Propulsion Laboratory taken during the last week of August 1989. It shows a hallway crowded with people, scientists in short sleeves, reporters with notepads, engineers holding coffee, all of them turned toward television monitors mounted near the ceiling. Nobody is looking at anybody else. Every face in the frame is tilted up, lit faintly blue by the screens. That was the posture of the entire building for days. By Encounter Week, more than 1,000 journalists had descended on Pasadena. Vice presidents and senators came. So did Chuck Berry, and I promise that detail will make sense before this chapter ends. On those screens, images were arriving from 4 billion kilometers away, each one composed of numbers, radioed home at the pace of a whisper. 4 hours and 6 minutes old by the time it existed on Earth at all. And the pictures were astonishing. The approach had already delivered the headline. The far, frozen planet had furious weather. Now, closing in, the cameras resolved the details. The great dark spot, that Earth-sized oval storm in the southern hemisphere, was not just sitting there. It churned, rolling counterclockwise, its edges fraying and reforming, its shape flexing on an 8-day rhythm like something breathing. Above it floated clouds that stopped the imaging team in their tracks. Bright, white streaks of methane ice crystals, so high above the blue deck below that they cast visible shadows down onto it, like cirrus clouds over a summer ocean, 50 kilometers of open air between the cloud and its shadow. People had expected at best a smoggy billiard ball. They were looking at a sky. There was the Scooter, the small bright cloud lapping the planet at its own quick pace. There was a second dark storm further south, with a bright core, promptly nicknamed Dark Spot 2. There was a fast, thin jet of cloud around the South Pole. The whole planet, it turned out, was banded, layered, restless, a world where, as one scientist put it that week, the weather report actually mattered, and it was written in winds nobody yet believed. because the numbers coming out of the cloud tracking were, frankly, embarrassing. Not embarrassing for Neptune, embarrassing for every atmospheric model on Earth. The clouds were racing. The measurements kept implying wind speeds of hundreds of meters per second on the planet that received the least sunlight of any world ever studied. For a while, people quietly assumed an error. There was no error. We will spend a whole chapter on those winds because they have still not been fully explained. While the cameras watched the weather, the other instruments were making their own discoveries, hour by hour. 6 new moons, all small, all dark, all orbiting close to the planet, doubling Neptune's known family in a single week. The largest of the 6, a lumpy, sooty world about 400 kilometers across, was named Proteus. It orbits so close to Neptune, lost in the glare, that no telescope on Earth had ever caught it. Remember Proteus? A scar on its side becomes important in a later chapter. And the rings. For a decade, astronomers had suspected Neptune had something ring-like because of a maddening series of observations from Earth. When Neptune passed in front of background stars, the starlight sometimes dipped briefly on one side of the planet, as if grazing something, but not on the other. Rings that only existed on one side? The proposed answer was ring arcs, incomplete segments, curved fragments of a circle. The trouble was, that should be impossible. Basic orbital mechanics says a clump of ring debris should smear itself into a complete, uniform circle within a few years at most. Voyager settled it. Neptune has rings. Full circles, in fact, 5 or so of them, but so faint, so starved of material, that from Earth they were undetectable except where one ring thickens into 3 or 4 dense, bright arcs, bunched along a single stretch like beads crowded on a wire. The impossible arcs were real. Something was holding them in place. The best answer, a gravitational shepherd, waits for us in the chapter on Neptune's kingdom, and it is elegant. All of this, the storms, the moons, the arcs, was pouring in while the spacecraft itself swept onward toward the moment everything had been aimed at for 12 years. First, though, the spacecraft had to survive the neighborhood. To thread its polar course, Voyager 2 had to cross the plane of those faint rings, the region where any stray debris would be waiting. A grain of dust, the size of a sand crystal, met at relative speeds of tens of kilometers per second, carries the punch of a rifle bullet. As the spacecraft sliced through the ring plane, its plasma wave instrument, an instrument built to listen to the faint electric crackle of space, began registering impacts. Hundreds of them. Tiny dust grains, far too small to harm the craft, were striking the body of the machine and vaporizing in microflashes, and the instrument heard each one. Engineers later converted that data stream into audio. It sounds exactly like hail on a tin roof, a squall of it, rising, peaking, and fading as the spacecraft punched through the plane and out the other side, unharmed. Somewhere in the archives of NASA, there is a recording of what it sounds like to fly through the rings of Neptune. I find it strangely comforting. At the far edge of the solar system, weather on the way in, weather on the way out. Closest approach came at 3:56 in the morning, Universal Time, on August 25, 1989, just before 9 in the evening on the 24th, Pasadena time, with the building full and the parking lots overflowing. Voyager 2 crossed over Neptune's North Pole, 4,950 kilometers above the clouds. After a journey of 7 billion kilometers, it arrived 35 kilometers off its aim point, about 20 miles, and within 1 second of the arrival time engineers had projected. I want to say that again because I don't think there is a more beautiful statistic in the history of navigation. 12 years, 7 billion kilometers, 4 gravitational slingshots. Final error, 1 second. People sometimes ask what the point of precision is, why engineers obsess over decimal places. That number is the answer. Precision is how a refrigerator bulb visits 4 planets on 1 tank of fuel. But here is the strange, quiet truth about that night, the one I keep returning to. At the moment the room in Pasadena celebrated closest approach, nothing they could see on their screens was current. The spacecraft had already crossed the pole 4 hours earlier. It had already threaded whatever dangers the ring plane held. It had already survived, or not. It was already diving down the far side of the planet toward its rendezvous with Triton. The cheering was for light. Everyone in that room was applauding the past, trusting, but not yet knowing, that the machine beyond the light was still alive. That is what exploring at 4 billion kilometers means. You do not steer, you cannot rescue. You plan for a decade, and then you sit in a crowded room with cold coffee, watching 4-hour-old light, waiting to learn whether the future you engineered actually happened. It had. The spacecraft came through the polar pass in perfect health, its instruments drinking in data, including measurements of one more Neptunian oddity that had the magnetometer team scratching their heads. The planet's magnetic field was wildly tilted and shoved off-center, as though someone had installed the planet's compass drunk. That mystery, too, gets its own chapter, because the answer probably involves an ocean unlike anything on Earth. 5 hours past the pole, Voyager 2 swept within about 40,000 kilometers of Triton, the stolen moon, the true prize of the trajectory. And what it saw there was so strange, so unexpectedly alive, that I am going to hold every detail of it for its own chapter later tonight. I will say only this. Of all the discoveries of that final encounter, Triton was the one nobody was prepared for. And then, it was over. Not gradually, not with a farewell orbit. Over, at more than 60,000 kilometers per hour, on a path bent forever downward, out of the plane of the planets, into the empty south. Neptune's gravity had done its final work, flinging the spacecraft onward one last time. Except this time, there was no next world at the far end of the arc. There is no next world. Voyager 2 had run out of solar system. In the days that followed, the spacecraft turned its cameras back for a last sequence of departure images. Neptune as a shrinking crescent, a blue fingernail of light, with Triton a smaller crescent beside it. 2 worlds, lit from behind, falling away. For my money, it is one of the most beautiful photographs of the 20th century. The last page of a family album, and the first page of a silence that has now lasted 37 years and counting. Back in Pasadena, on the night of the 25th, they held the celebration. And this is where Chuck Berry comes in, because his song, Johnny B. Good was one of the pieces of music carried on the golden record, the message in a bottle bolted to Voyager's side. So when the last planet was passed, and the last pictures were safely home, Chuck Berry himself stood on a stage at the Jet Propulsion Laboratory, in front of the scientists and engineers of the longest road trip in human history, and played the machine out of the solar system. Engineers who were there described dancing with strangers, and a strange double feeling that no one could quite name. The proudest night of their professional lives, and the end of something that would never, in their working lifetimes, come again. One of them later called the whole Neptune encounter the last picture show. Within weeks, most of Voyager 2's cameras were commanded off, their software eventually deleted to save memory and power for the long interstellar cruise. There was nothing left out there to photograph. The optical story of the mission, 12 years, 4 planets, tens of thousands of images, closes at Neptune. The blue planet is the last thing the Great Tour ever truly looked at, which leaves us, and science, exactly where that August left us, holding one long night of data from a world that then went back to being a dot. The rest of tonight's journey is about what was inside that data, and what 37 years of squinting from Earth have added since. And it begins with the finding that broke the textbooks: the wind. Let us start this chapter with a simple, honest question. How do you measure the wind on a planet 4.5 billion kilometers away? You cannot put out a weather vane. No probe has ever descended into Neptune's air. Every wind speed you have ever heard quoted for this planet was measured from photographs. Here is how. You take an image of Neptune. You find a cloud, a bright methane streak, a dark storm, the little scooter. You note exactly where it sits. Then you take another image hours later, and you find your cloud again, and you measure how far it has traveled. Distance divided by time. The same arithmetic you would use to time a friend walking down the street, applied across 4 billion kilometers to clouds the size of continents. You also need to know what the planet beneath the clouds is doing, because a wind is only a wind relative to the ground, and Neptune has no ground. The reference is the planet's rotation, which betrays itself through the magnetic field. The deep interior of Neptune turns once every 16 hours and 7 minutes. That is the planet's day. Anything moving faster or slower than that rotation is, by definition, wind. Voyager's imaging team did this arithmetic in August 1989, cloud by cloud, frame by frame. And the numbers refused to be reasonable. Near the equator, the clouds were sweeping backwards, against the planet's rotation, at some 400 meters per second, 1,400 kilometers per hour. Toward the poles, the flow reversed, running eastward. And in the shear zones around the Great Dark Spot, the relative speeds climbed further still. Peak winds on Neptune reach roughly 2,100 kilometers per hour, about 1,300 miles per hour. I want to give those numbers a body because they slide past the ear too easily. The strongest hurricane gust ever measured on Earth is on the order of 400 kilometers per hour. The most violent tornadoes, the ones that erase towns, spin at around 500. Neptune's everyday equatorial jet is 3 times faster than the worst tornado. Its peak winds are 5 times a Category 5 hurricane. Here on Earth, at sea level, sound travels at about 1,225 kilometers per hour. Neptune's winds comfortably exceed that. If you could stand in that flow, you cannot. There is nothing to stand on. But come with me anyway. The air around you would be moving faster than the crack of a whip, faster than the shock wave of thunder travels, a wind that outruns sound. There is one more comparison worth making because it is close to home. In 2015, Hurricane Patricia in the eastern Pacific became the strongest hurricane ever measured on this planet, with sustained winds near 345 kilometers per hour. Cities were evacuated. Meteorologists called its intensity almost incomprehensible. Neptune's ordinary, everyday climatological equatorial wind, not a storm, not an event, just the standing weather, is 4 times faster than the strongest hurricane in recorded human history. On Neptune, Patricia would read as a stall in the breeze. And now put that fact next to the other fact, the one we have been carrying since the first chapter. This is the planet that receives 1/900th of the Earth's sunlight, the planet where noon is twilight, the coldest cloud tops ever measured on a giant world, around -218 degrees Celsius. Sunlight is supposed to be the engine of weather. It heats the tropics more than the poles. The atmosphere stirs itself, trying to even out the difference. Storms and winds are the machinery of that stirring. More sunlight, more violence. That is the intuition, and within the inner solar system, it roughly holds. Jupiter, with 4% of Earth's sunlight, but a vast internal furnace, manages winds around 500 or 600 kilometers per hour. Saturn does better, up to 1,800. Then comes Neptune, with a fraction of Saturn's light, and it beats everyone. The solar system's speed record for wind belongs to its dimmest, coldest major world. That is not a poetic exaggeration. It is a plain observational fact, and it has been sitting in the data for 37 years like a splinter. Part of the answer, most scientists believe, lies underfoot. In 1966, long before Voyager, astronomers measuring Neptune's infrared glow noticed it seemed warmer than sunlight alone could make it. Voyager confirmed it precisely. Neptune radiates about 2.6 times more energy than it receives from the sun. Let me say that carefully. For every unit of heat the Sun delivers to Neptune, the planet sends 2.6 units back out into space. The difference is coming from inside. Neptune is not just reflecting a fire 4.5 billion kilometers away. Neptune has its own fire, faint, deep, and old. Where does internal heat like that come from? The standard answer is leftover warmth. A giant planet is built by collapse. Gas and ice falling together, compressing, and compression makes heat. 4.5 billion years later, that primordial warmth is still leaking out, the way a loaf of bread stays warm long after the oven, if the loaf were 17 Earths of mass wrapped in insulating atmosphere. As the planet slowly contracts, even by tiny amounts, gravity keeps converting that shrinkage into fresh heat. And there may be a stranger contribution. A slow rain of diamonds sinking through the interior, releasing energy as it falls. But I am saving the diamonds for the chapter they deserve. That internal fire explains part of the paradox. Neptune's weather engine is not solar-powered. It runs from below. The temperature difference between the warm, deep interior and the frigid cloud tops drives convection. Heat rising, churning, stirring the atmosphere from underneath, with sunlight as a mere garnish on top. But that cannot be the whole story, and I want to show you why. Because the counterexample is one of the most delicious in planetary science. Neptune has a twin. Uranus is almost the same size, almost the same mass, made of almost the same stuff. It is closer to the Sun, so it receives more than double Neptune's sunlight. If weather were about energy supply, Uranus should be at least as lively. Uranus, when Voyager 2 flew past in 1986, was the blandest world the mission ever saw. A fogged, featureless teal billiard ball, its winds respectable but modest, its cloud deck nearly unmarked. And here is the key measurement. Uranus radiates only about 1.06 times what it receives, essentially nothing. Of the 4 giant planets, 3 have strong inner fires. Jupiter, Saturn, Neptune, and 1, Uranus, sits cold. Why Uranus's furnace is out, whether some ancient collision emptied it early, or its interior is layered in a way that traps the heat inside like a lid on a pot, is a genuinely open question. Nobody knows. So the twins deliver a controlled experiment. The twin with inner heat has the fastest winds in the solar system. The twin without it barely has visible weather. Neptune's violence is not an accident of distance or size. It is powered from within. And yet, the splinter stays in. Because even granting the inner fire, the total energy budget of Neptune's atmosphere is tiny. Sunlight, plus all the internal heat together, amount to a trickle compared with what Earth's atmosphere receives. Running the fastest winds in the solar system on that trickle is like hearing a chainsaw roar and then being told it runs on a watch battery. The resolution, as best we currently understand it, and I will flag honestly that this is understanding, not certainty, is that Neptune's winds are not about power. They are about the absence of brakes. Think about what stops wind on Earth. Friction with the ground, hills, forests, waves, cities, all dragging the moving air to a halt. Turbulent weather itself. Storms churn the atmosphere vertically, mixing fast layers with slow ones, smearing away momentum. Every windstorm on Earth is being actively strangled from below. Neptune has no ground. No surface exists anywhere on the planet. The atmosphere simply thickens downward into fluid, as we will see in the interior chapter. There is nothing for the wind to rub against, and the winds themselves appear to be shallow. This is one of Voyager's subtler gifts. By measuring exactly how the spacecraft was tugged as it flew past, and combining that with the planet's shape, scientists could probe how deep the winds reach. The answer, refined over the years, the racing jets are confined to a relatively thin outer shell, the outermost fraction of a percent of the planet's mass, perhaps the top 1,000 kilometers or so. Below that, the interior seems to rotate placidly, almost as one body. the hurricane is only skin deep. Cold, it turns out, helps rather than hinders. A very cold atmosphere is a smooth atmosphere, less turbulent, small-scale churning, less of the frothy chaos that eats momentum. Some scientists describe Neptune's upper atmosphere as one of the most nearly frictionless natural systems known. So assemble the picture. A thin, ultra-cold, ultra-smooth shell of air. A gentle but ceaseless push of heat from below, and almost nothing, no surface, no drag, no brakes to ever slow anything down. Push a swing with no friction, even weakly, and push it for 4.5 billion years. The speed you end up with does not reflect the strength of the push. It reflects the patience of it. Neptune's winds, in this picture, are ancient. Momentum banked over geological time, spent on nothing, dissipated nowhere. A flywheel the size of a planet, spun up over eons, still accelerating for all we know. The fastest winds in the solar system are not a storm in any earthly sense. They are a savings account. I find something restful in that, oddly enough. On Earth, violent wind means emergency, something sudden, something breaking. Neptune's wind is the opposite of an emergency. It is the same wind that was blowing when the dinosaurs died, when the first fish crawled ashore, perhaps when the Earth itself was young. Nothing on Neptune is in a hurry. Even its fury is patient. I should add one honest footnote about color. The famous Voyager pictures show Neptune as a deep, saturated azure, and that color became the planet's identity. In 2024, researchers went back to the original data and showed that the processing of those images had exaggerated the blue. The real Neptune, seen plainly, is a paler, milkier blue, closer to Uranus's shade than the posters suggest, tinted by methane, which swallows red light. I will keep calling it the blue planet because it is one. Just know that, like everything else from that single night in 1989, even the color has taken decades of second looks to get right. The winds, though, survived every second look. The storms did something stranger. They started disappearing. That story of vanishing spots, of clouds that dissolved planet-wide while astronomers watched, and of weather that answers to the sun in a way nobody predicted, is next. When Voyager 2 left Neptune behind in August 1989, it left a planet with a face. The great dark spot, that churning, Earth-sized oval, had become Neptune's signature, printed in every newspaper and textbook. It looked permanent. It looked, in fact, like a little sibling of Jupiter's Great Red Spot. And the Great Red Spot has been raging for at least 200 years, probably far longer. Astronomers reasonably assumed Neptune's dark eye would be there, staring back, whenever we looked next. For 5 years, nobody could check. No telescope on Earth could see detail that fine across 4.5 billion kilometers. Then, in the early 1990s, the Hubble Space Telescope came online, and after its optics were repaired in late 1993, it could finally resolve Neptune's disk sharply enough to look for the storm. In June 1994, Hubble turned toward Neptune. The scientists pulled up the images. The great dark spot was gone. Not shrunken, not drifted. Gone, dissolved without a trace in less than 5 years. An anticyclone the size of the Earth, with winds tearing around its rim at hundreds of meters per second, had simply closed like an eye and left blank blue cloud where it had been. And then, within a year, Hubble found a new dark spot. In the northern hemisphere this time, a hemisphere away from the original. Neptune had not lost its weather. It had shuffled it. That pair of observations quietly rewrote what kind of planet Neptune is. Jupiter's storms are ancient institutions. Neptune's, it turns out, are mayflies. Enormous, ferocious mayflies. In the decades since, astronomers have watched dark spots appear, wander, and die at least half a dozen times. They seem to be born at mid-latitudes, live for 2 to 6 years or so, and vanish. Each one is a vortex the size of a continent or larger. Each one comes with its own entourage of bright, high methane clouds condensing at its edges, like white feathers around a dark eye. Watching them has produced real drama. The finest specimen arrived in 2018, when Hubble caught a fresh, dark storm in the northern hemisphere, about 7,400 kilometers across, wider than the Atlantic Ocean. Astronomers tracked it season after season, and what they saw broke the pattern. In 2019, the storm began sliding toward the equator, which, according to every model, is a death sentence. The physics that holds these vortices together weakens toward the equator. Storms that drift there are expected to unravel like knitting. This one approached the danger zone, slowed, and then reversed. It turned around and climbed back toward the pole, the first storm ever observed to change its mind. And as it turned, it shed a piece. A smaller, dark fragment, promptly nicknamed Dark Spot Jr., that broke away and wandered off on its own before fading. A storm calving a storm. Nobody had seen anything like it, on any planet. I want to pause on something hiding inside this story, because I think it is easy to miss. Every one of those observations came from Earth orbit, or from the ground. After 1989, planetary science at Neptune became a discipline of squinting, of wringing knowledge out of a disk 2 arcseconds wide. And the squinting kept getting better. In 2023, for the first time, a dark spot was detected not by Hubble, but by a telescope standing on the ground. The Very Large Telescope in the mountains of Chile, whose instruments can now split Neptune's faint light finely enough to probe the storm's depth. That study answered a 30-year-old question about what the dark spots actually are. They are not holes in the clouds, as many had suspected, not windows into a deeper, darker layer. They appear to be regions where a haze layer below the visible clouds darkens, like a bruise beneath the skin. The spot is not an absence, it is a shadow within. The ground-based revolution deserves a sentence of appreciation, because it borders on magic. The reason telescopes on Earth struggle is not size. Our mirrors dwarf Hubble's. It is the air. Earth's own restless atmosphere smears starlight the way summer heat shimmers a distant road. That shimmer is why stars twinkle, and why fine detail on a tiny disk like Neptune's dissolves. The cure is called adaptive optics, a deformable mirror driven by computers that flexes its surface hundreds of times per second to precisely unbend the incoming light, canceling the atmosphere's ripples in real time. With that trick, the great observatories in Chile and Hawaii can now photograph Neptune's storms from sea-level Earth, through 4.5 billion kilometers of space and the last 100 kilometers of wobbling air, nearly as sharply as Hubble does from orbit. Astronomers on a mountaintop, watching hurricanes on a world where no one has stood, by teaching a mirror to tremble in exactly the opposite way the sky trembles. We have learned to untwinkle the stars. And then, while everyone was watching the storms, the clouds themselves staged a vanishing act. Astronomers have been photographing Neptune systematically for about 3 decades now, long enough, finally, to study its moods rather than its moments. Around 2019, observers noticed the planet's bright methane clouds thinning. Through 2020, the thinning became a rout. Within months, nearly all the visible clouds on the entire planet dissolved. A world that in 1989 had been streaked with silver cirrus went almost naked, a bare blue globe with only a stubborn cap of cloud clinging near the South Pole. Longtime Neptune observers described the images as barely recognizable. Even the amateurs saw it, Neptune visibly dimmed in backyard telescopes, because the bright clouds are a large part of what reflects its sunlight back to us. Why? The answer, published in 2023 after a careful trawl through 30 years of imagery, is one of my favorite recent results in all of planetary science, because it connects the dimmest planet to the brightest possible cause. Neptune's cloud cover, it turns out, rises and falls in step with the sunspot cycle, the sun's own 11-year heartbeat of magnetic activity. When the sun is active, flooding space with ultraviolet light, Neptune's clouds bloom, with a lag of about 2 years. When the sun goes quiet, the clouds fade. The 2019 collapse followed a deep solar minimum right on schedule. And as the sun climbed toward its next maximum, the clouds duly began returning in 2023. Think about what that means. At Neptune's distance, sunlight is a rumor, 1/900th of what you feel on your face at noon. And yet the faint ultraviolet edge of that rumor is apparently enough to drive photochemistry in Neptune's high air. Enough, we think, to help seed the condensation of methane ice, and the whole planet's complexion follows the sun's pulse like a tide follows the moon. The farthest planet is still, visibly, one of the sun's children. Even in the dark at the edge of the park, the grapefruit on the table calls the tune. It is worth noting the honest footnote. This correlation spans only about 2.5 solar cycles of data, because that is all the sharp imagery we have. Neptune's other clock, its 40-year seasons, each one a human career long, has barely ticked once since we started watching properly. Southern summer solstice came in 2005. Northern spring will not arrive until the 2040s. Somewhere in the data, a seasonal signal is probably hiding under the solar one, and nobody alive has seen even a single full Neptunian year of weather. We are reading a novel, 1 page per decade. I sometimes think about the astronomers this implies, the ones not yet born. Whoever writes the definitive book on Neptune's seasons will be stitching together observations made by their grandparents' generation with their own, trusting colleagues they never met, in a collaboration conducted across a century. Neptune enforces a kind of scientific humility that almost nothing else does. It simply will not fit inside one career. You do your shift of watching, you write down what you saw, and you hand the notebook forward. The newest eyes of all belong to the James Webb Space Telescope, and Webb has already delivered 2 gifts. The first was a portrait. In 2022, Webb photographed Neptune in the infrared, and because methane swallows infrared light, the planet's body appears as a dark, ghostly pearl, while the rings blaze. It was the clearest image of Neptune's rings since Voyager left. The full circles, the bright arcs, all hanging there exactly where 1989 said they would be, as if the intervening decades had been an afternoon. The second gift answered a 35-year embarrassment. Every giant planet has auroras, polar light shows where charged particles rain along magnetic field lines into the atmosphere. Jupiter's are spectacular, Saturn's and Uranus's are well documented. Neptune's had never been seen. Voyager caught hints in 1989, and then, for 3.5 decades, nothing, despite repeated searches. In 2025, Webb finally caught them, by detecting the infrared glow of an exotic molecule, a charged form of hydrogen. 3 hydrogen nuclei bound around 2 shared electrons, that forms where auroral particles strike the upper air. 2 things about the discovery are wonderful. First, the reason the auroras had been so hard to find. Neptune's upper atmosphere has cooled dramatically since 1989. Its ionosphere is only about half as hot as when Voyager measured it, and cooler gas glows far more feebly. The lighthouse had been turned down low while we were busy building better eyes to see it. Nobody fully knows why. Another entry in Neptune's ledger of open questions. And second, the auroras are not where auroras are supposed to be. On Earth, they ring the poles. Neptune's glow at mid-latitudes, roughly where South America sits on Earth, because the planet's magnetic field is so wildly tilted that its magnetic poles point nowhere near its geographic ones. The lights are exactly where a drunken compass would put them, which is as good a door as any into the next chamber of the story. Because that broken compass is not a quirk. It is a message from the interior, from a place where water forgets how to be water, where the pressure of an ocean thousands of kilometers deep squeezes chemistry into forms unknown on Earth, and where, if the experiments are right, it rains diamonds onto a core as hot as the surface of the sun. Time to go inside. Every world we have visited so far tonight, you could at least imagine standing on. Not this one. So let us do the descent properly, slowly, in thought, the only vehicle that will ever survive the trip. We start where the photographs stop, at the cloud tops, in that twilight blue, minus 218 degrees, the supersonic wind carrying us sideways like a leaf in a river. The pressure here is about the same as at sea level on Earth. This is the last place on Neptune that resembles anything you know. Now we sink. For the first few hundred kilometers, it is merely a stranger version of familiar things. The air is hydrogen and helium, seasoned with methane, the gas that eats red light and paints the planet blue. We fall past decks of methane clouds, then, deeper, clouds that chemists believe are hydrogen sulfide, the smell of rotten eggs, though there is no one to smell it. Then likely clouds of ammonia, and deeper still, clouds of water. The pressure climbs. Tens of Earth atmospheres, hundreds. The last daylight gave out long ago. We fall through absolute black, the temperature rising steadily around us, the gas thickening. Some markers, so you can feel the depth. The finest military submarines on Earth begin to fail at about 50 or 60 atmospheres of pressure. We pass that point while still falling through what looks in every direction like mere sky. The crushing pressure at the bottom of the Mariana Trench, 1,100 atmospheres, the weight that flattens unprotected steel, comes and goes while we are still, technically, in Neptune's atmosphere. There is no drama at these thresholds, no boundary, no jolt, just the quiet arithmetic of depth on a world built entirely out of deep. And here Neptune quietly abandons every category you brought with you, because there is no moment, none, where you would ever land. On Earth, sky and sea are different things. There is a surface, a boundary, a place where one ends and the other begins. On Neptune, the atmosphere simply thickens. The gas grows denser and hotter until, without any border, it stops behaving like gas and starts behaving like liquid, a state physicists call a supercritical fluid, which is not quite either and is both. If you dropped a probe, it would never splash down. It would just find itself at some point no longer falling through air, but suspended in an ever-thickening hot fluid, like a bead of glass sinking into honey that gets hotter and heavier forever. There is no ground floor. Hold on to that. A planet 17 times the mass of Earth, and nowhere in it a single solid place to put your hand, until the very center, and we are not there yet. A few thousand kilometers down, we enter the layer that gives Neptune its family name. Astronomers call Neptune and Uranus ice giants, and the name misleads everyone, so let me clear it up. There is no ice here, nothing frozen, nothing cold. The interior is thousands of degrees. Ice, to a planetary scientist, is just a word for a particular family of molecules: water, methane, ammonia, regardless of temperature. Jupiter and Saturn are mostly hydrogen and helium, the sun's own recipe. Neptune is mostly this other stuff, an immense, deep ocean of hot, compressed water, ammonia, and methane. Perhaps 80% of the planet's mass is this searing fluid mantle. If you want a picture of Neptune, forget the marble of blue gas. Picture an ocean perhaps 15,000 kilometers deep, 1,000 times deeper than the deepest trench in the Pacific, with no floor you could name and no shore anywhere, wrapped in a thin rind of sky. That ocean conducts electricity. The ammonia and water are squeezed into an ionic soup, their molecules stripped and charged. Remember that. It becomes the answer to the compass mystery in a few minutes. First, though, the diamonds. I promised you diamonds. Deep in that mantle, thousands of kilometers down, at temperatures of several thousand degrees and pressures hundreds of thousands of times Earth's atmosphere, methane itself begins to fail. A methane molecule is one carbon atom holding 4 hydrogens. Under enough heat and pressure, the grip breaks. The hydrogen wanders off, and the carbon atoms, freed and crushed, do what carbon atoms do under crushing pressure. They become diamond. Not gem-cut stones, nucleating crystals, growing as they drift. And diamond is denser than the fluid around it, so the crystals sink. A slow, continuous precipitation of diamond, falling through a black ocean toward the center of the planet, growing as it goes. How large the falling diamonds get, nobody knows. Estimates run from nanoscale grit to, in the more excitable calculations, stones of enormous size. It has been raining this way, plausibly, for 4 billion years. I want to be careful here, the way I promised to be. No instrument has ever seen inside Neptune. This is theory, but it is tested theory, and the tests are wonderful. In 2017, at the SLAC laboratory in California, researchers took polystyrene, a plastic chosen because it is made of carbon and hydrogen, methane's chemical cousins, and hit it with pulses from the most powerful X-ray laser on Earth, slamming it for a few billionths of a second into the temperature and pressure of Neptune's mantle. And in those few billionths of a second, the X-rays watched nanodiamonds crystallize out of the plastic. The diamond rain works. We have run a raindrop's worth of Neptune's weather in a basement in California and watched the diamonds form. The experiments have kept going, and they keep making Neptune's version of weather more plausible, not less. In later runs, researchers switched from polystyrene to PET, the ordinary plastic of soda bottles, because it contains oxygen alongside the carbon and hydrogen, a closer match to Neptune's true chemistry. The diamonds formed more readily, not less. Oxygen, it turns out, helps strip the hydrogen away and freeze the carbon to crystallize at gentler pressures than anyone expected. Which means diamond rain may begin at shallower depths, across a thicker slice of the planet than the first models dared to suggest. Somewhere below us, in other words, the forecast is diamonds, heavier than previously reported. There may be more than rain down there. Some models suggest that at the boundary where the mantle meets the core, the diamonds accumulate, that Neptune may have, in effect, diamond snowdrifts thousands of kilometers deep, or even a shell of diamond settling around its heart. And the falling itself matters. Every sinking crystal converts a little gravitational energy into heat, feeding, perhaps, that mysterious inner fire, the 2.6, that drives the fastest winds in the solar system. It would be a tidy piece of poetry if it closes, the winds at the top of the sky powered, in part, by diamonds falling at the bottom of the sea. Deeper still, the water itself gives up being water. At pressures approaching 1 million Earth atmospheres, laboratory experiments breathingly, shock waves, and laser cells, in the last decade, have confirmed a state of matter physicists had predicted on paper back in 1988. Superionic ice. The oxygen atoms lock into a rigid crystal lattice, a true solid. But the hydrogen atoms detach and flow, streaming freely through the oxygen scaffold like a liquid pouring through a jungle gym. It is ice and ocean simultaneously, solid and liquid, both at once, black and hot, thousands of degrees, and utterly stable at depths where nothing familiar survives. Nothing like it exists naturally anywhere on Earth. Inside Neptune, there may be more superionic ice than there is ordinary rock in all the terrestrial planets combined. And now, at last, the compass. When Voyager 2 crossed Neptune in 1989, its magnetometer delivered one of the mission's genuine shocks. Earth's magnetic field is tidy, roughly aligned with the spin axis, roughly centered in the planet, which is why a compass points north. Neptune's field is tilted 47 degrees from its rotation axis, as if Earth's magnetic north pole sat in the Mediterranean, and it is not even centered in the planet. The field's effective origin is displaced from Neptune's center by more than half the planet's radius, closer to the cloud tops than to the core. A compass on Neptune would be worse than useless. The field's strength varies more than tenfold between hemispheres, and as the planet turns its 16-hour day, The whole lopsided magnetic bubble around it tumbles and reshapes itself continuously, like a bell tent in the wind. For a while, this looked like a fluke, until Voyager reached Uranus and found its field almost equally strange. Two drunken compasses is not coincidence. It is a mechanism. The favored explanation lives in that electric ocean. Earth's field is generated deep in its core by convection in liquid iron, a dynamo running at the planet's heart, which is why the field comes out centered and orderly. Neptune's dynamo, the evidence suggests, does not run in its heart. It runs in a comparatively thin, churning shell of that ionic water-ammonia ocean, at shallow depths, with the sluggish superionic layers below possibly refusing to convect at all. A dynamo running in a thin offset shell naturally produces exactly what Voyager measured: a field tilted, off-center, messy, and restless. The broken compass is not broken. It is a sounding line, the clearest evidence we possess for what the inside of an ice giant actually is. Not layers of quiet onion, but a shallow electric sea over a strange, solid, liquid deep. At the very bottom of everything, some 6,000 or 7,000 kilometers from the center, sits the core. Rock and metal, roughly the mass of the Earth or a little more, compressed under some 7 million atmospheres. Its temperature is around 5,000 degrees Celsius, about the temperature of the surface of the Sun. Sit with that final image for a moment, because I think it is the strangest one Neptune offers. At the heart of the coldest, dimmest major planet, beneath the twilight clouds and the supersonic winds, beneath the bottomless ocean and the diamond rain and the ice that flows, there is a ball of rock the size of the Earth, glowing at the temperature of a star's face, in a darkness that has never once, in 4.5 billion years, been interrupted by light. A buried, invisible sun, wrapped in the deepest ocean in the solar system. And in orbit around all of this, around the storms and the strange sea and the secret fire, circles the moon that should not be there, the moon that orbits backwards, the moon Neptune stole. Its story is next, and I have been saving it all night, because I think it is the best one. 17 days after Neptune was discovered, an English brewer found its moon. William Lassell made his fortune in beer and spent it on telescopes. He was one of the finest amateur astronomers who ever lived, in an age when the word amateur carried no sting. When news of the Berlin discovery reached England in October 1846, Lassell pointed his 24-inch reflector at the new planet, and on October 10th, he caught a faint point of light keeping station beside it. A moon. It would eventually be named Triton, for the sea god's sun. For a century, Triton was just that point of light. But as measurements sharpened, the point of light revealed a secret. And the secret was scandalous. Triton orbits Neptune backwards. Every large moon in the solar system, ours, the 4 great moons of Jupiter, Titan at Saturn, all of them, orbits in the same direction its planet spins. This is not a coincidence. It is a birthmark. Planets and their moons condense from the same spinning disk of material, like a family formed from one whirlpool, and so they all turn together. It is among the most reliable rules in celestial mechanics. Triton breaks it. Neptune spins one way. Triton, a giant moon, 2,700 kilometers across, bigger than Pluto, one of the 7 great moons of the solar system, circles it in the opposite direction. Retrograde, astronomers say. Backwards. A moon cannot be born backwards, which leads to a conclusion as inescapable as it is dramatic. Triton was not born here. Neptune did not make this moon. It caught it. Where did it come from? The answer connects our whole story together. Beyond Neptune stretches the Kuiper Belt, that vast ring of small frozen worlds at the edge of the planetary system, the neighborhood Pluto belongs to. Triton, nearly every line of evidence agrees, is a Kuiper Belt object, a big one, a sibling of Pluto, the same size class, the same icy recipe of nitrogen and methane frosts over rock. Long ago, probably in the solar system's chaotic youth, this Pluto-like world wandered too close to Neptune and was seized. Capturing a moon is not gentle. An incoming world moving too fast will simply swing past. To be caught, it must shed enormous energy. The leading idea is that Triton arrived as half of a binary pair, two worlds orbiting each other, as Pluto and its companion Charon do today. When the pair swung past Neptune, gravity split them. One partner was flung away at speed, carrying off the excess energy, and the other, Triton, was left behind, trapped, swinging into a wild, backwards orbit around its captor. Think about the violence hidden in that sentence. Whatever family Neptune had made for itself before, whatever original moons had condensed from its birth disk, Triton arrived among them like a cannonball through a greenhouse. Its early orbit was huge and eccentric, sweeping through the whole satellite system. Over the ages that followed, collisions and gravitational stirring destroyed or scattered nearly everything that had been there first. The small inner moons we met in the Voyager chapter are, in the standard picture, not survivors. They are rubble, reassembled from the wreckage after Triton's arrival. And one relic of the chaos still hangs in the sky. Nereid, the moon found in 1949, rides the most lopsided orbit of any large moon known, swinging from 1.4 million to 9.7 million kilometers from Neptune, a sevenfold breathing of distance, very plausibly a scar of the catastrophe, an original moon kicked half loose and never recovered. Then, over hundreds of millions of years, tides did their patient work. Neptune's gravity kneaded the captured world. Friction bled its wild orbit down into the nearly perfect circle we see today. And that kneading had a consequence. The young Triton must have been heated ferociously, melted, resurfaced, perhaps kept warm with a buried ocean for a very long time. Hold that thought too. There may be one more consequence, and it is brand new. In March of 2026, a few months ago, as I record this, a dynamicist published calculations suggesting that Triton's long, slow tidal spiral did something even grander than rearrange the moons. It may have tipped the whole planet. Neptune's spin axis leans about 28 degrees, and in these simulations, the drawn-out gravitational tug-of-war with its captured moon is enough over time to have rocked the giant itself into that lean. I want to flag this honestly as a fresh proposal. Not settled science, it has not yet survived years of scrutiny. But if it holds, then the seasons of Neptune, those 40-year seasons we spoke of, are themselves a souvenir of the kidnapping. The stolen moon reshaped its captor. The burglar rehung the paintings. So, that was the world Voyager 2 was aimed at, 5 hours after the polar pass, the reason the trajectory bent so low over Neptune in the first place. In August 1989, nobody on Earth knew any of what I just told you beyond the backwards orbit. Triton was a fuzzy, pinkish dot and a set of suspicions. Many scientists expected a dead ball of ice. At 30 times the Earth's distance from the Sun, what else could it be? What the cameras actually returned in those 5 hours remains, for my money, the most surprising portrait of the entire 12-year mission. The first shock was the temperature. 38 degrees above absolute zero, minus 235 Celsius. At the time, the coldest surface ever measured on any world in the solar system. Cold enough that nitrogen, the gas that makes up most of every breath you take, lies frozen solid on the ground as gleaming frost. The second shock was the face. Triton's surface is young, almost no craters, and a world with few craters is a world that repaves itself. Instead, the cameras found terrain like nothing seen before or since, rolling fields of dimpled, puckered ice that the geologists, reaching for any comparison, named cantaloupe terrain, because it genuinely looks like the skin of a melon. Long frozen lakes of once liquid material, ridges and furrows like frozen weather. An active, worked-over, living landscape on a captured moon at the edge of everything, where every textbook said geology should have died billions of years ago. And then came the plumes, and with them, one of the great moments of the space age. Examining the images of Triton's south polar cap, scientists found dark columns rising straight up off the surface, rising 8 kilometers, 5 miles, into the thin air, then bending at the top and streaming away downwind for 100 kilometers or more, like smoke from unseen chimneys. Dozens of dark streaks fanned across the polar frost, the fallout of plumes past and present. Geysers. On a world colder than liquid nitrogen, something was erupting. The favored explanation is elegant enough to tell a child. Triton's polar cap is nitrogen ice, and nitrogen ice is translucent. Feeble as it is, sunlight passes through the clear ice and warms the darker material trapped beneath, and the heat cannot easily escape back through the ice above. A greenhouse, made of glass ice, on a world where the sun is a bright star. A few degrees of warming is enough. Buried nitrogen turns to gas, pressure builds beneath the cap, and where the ice cracks, the pent-up gas roars upward in a column, carrying dark dust with it, until it hits the thin winds aloft and smears into that long, horizontal plume. Solar-powered eruptions, running on 1/900th of the light that reaches your window. Voyager caught at least 2 of them erupting live in a single afternoon from one hemisphere. Triton, the frozen, captured, backwards moon, turned out to be one of the very few worlds in the solar system where we have watched eruptions happen. Earth, Io, Enceladus, Triton. That is the whole list, more or less. And Triton earned its place on it during a 5-hour visit. There is likely more beneath. The same tidal kneading that circularized Triton's orbit baked it thoroughly in its youth. Combined with the slow warmth of radioactive rock in its interior, many scientists think Triton may still hold a liquid ocean under its ice, salty water, or a water-ammonia antifreeze, wrapped around its core in the dark. If so, it belongs on the short list of possible habitats in the solar system. An ocean world, one that came in from the Kuiper Belt, carrying who knows what chemistry from the outer dark. It is a genuinely open question, and it is one of the loudest scientific arguments for going back. One more detail because it makes Triton feel less like a museum piece and more like a place with a pulse. Triton has an atmosphere, a wisp of nitrogen, 70,000 times thinner than Earth's air, fed by the sublimating frost. Voyager measured it, and even photographed thin clouds and haze riding in it. And in the years after the flyby, when Triton drifted in front of distant stars, astronomers timing how the starlight faded found that the atmosphere had thickened. The frost was evaporating faster, the wisp growing, as Triton's south pole leaned into its decades-long summer. A world so cold it freezes the air you breathe, and it still keeps seasons. Its atmosphere inhales and exhales on a 40-year breath. Now I owe you a picture, the one a viewer of this channel asked for once, and the one I would most like to see myself. Stand on Triton. You are standing on pink-white nitrogen frost, in a silence so complete it has texture. The gravity is feather light. You weigh 1/12 of your Earth weight. The sun hangs among the stars, a hard, brilliant point, far too small to show a disk, yet still more than 400 times brighter than the full moon. Daylight of a kind, a pale silver noon that casts sharp shadows. The horizon curves close, only a few kilometers away, because this world is small. And above the horizon, filling the sky, is Neptune. It spans 8 degrees of the sky, 15 full moons across, side by side. A colossal, dim-lit blue-gray disk, its bands and storms faintly visible, hanging silently in the black. It does not rise or set. Triton keeps one face forever toward its planet, so from where you stand, Neptune simply hangs there, fixed, eternal, like a lantern nailed to the night. Over the nearly 6 days it takes the stars to wheel once around behind it, you might catch the drift of a bright methane cloud crossing that vast face, or the slow blink of a dark storm at its rim. Somewhere beneath your boots, a geyser is quietly building pressure under the glass ice. Somewhere above, a spacecraft's ashes of momentum still carry it away, 37 years gone. And the great blue disk overhead holds its place, patient as ever, keeping its stolen companion close. It will not keep it forever. But the end of that story, Triton's slow fall, and the spectacular thing Neptune will build from it, belongs to the next chapter, along with the rings, the shepherd moon, and the long, courtly dance Neptune leads with Pluto at the edge of the map. Every giant planet wears rings, but each wears them differently. Saturn's are a cathedral. Jupiter's are a breath of dust. Uranus wears thin, dark hoops, neat as pencil lines. And Neptune wears the ghost of a ring system. 5 faint circles of dust so tenuous that, if you gathered every particle of them together, the result would be smaller than a single modest moonlet. A ring system, by mass, that is barely there at all. The names alone tell you this planet's history belongs to people as much as physics. The rings of Neptune are called Gal, Leverrier, Lassell, Arago, and Adams. The astronomer who found the planet at the eyepiece, the mathematician who found it on paper, the brewer who found its moon, the physicist who coined the phrase about the point of a pen, and the young Englishman who calculated in parallel and lost the race. The whole discovery story from our second chapter, written in orbit around the planet itself. Science does not always remember its people well. Here, it remembered 5 of them with circles of light. The outermost ring, Adams, is where the mystery lives, the mystery that made these rings famous before anyone had seen them. Embedded in that thin circle are the arcs, 3 or 4 dense, bright segments bunched along one stretch of the ring like beads crowded together on a wire, with near emptiness along the rest of the circle. When French astronomers helped pin them down from Earth in the 1980s, they named them in the spirit of their republic: Liberté, Égalité, Fraternité. A 4th, smaller arc later took the name Courage, and they should not exist. We said it in the Voyager chapter, and it bears repeating with feeling. A clumped arc of orbiting debris is a chalkboard simple impossibility. Particles on slightly different orbits move at slightly different speeds. The inner ones lap the outer ones, so any clump must shear apart, smearing itself into a uniform ring within a few years. The arcs of Neptune stand there, clumped, decade after decade, in open defiance of freshman orbital mechanics. The resolution is a small moon with a shepherd's crook. Just inside the Adams ring circles Galatea, one of Voyager's 6 discoveries, a dark little body about 175 kilometers across. Galatea circles slightly faster than the ring material above it, in a precise gravitational rhythm. For every 43 orbits Galatea completes, the ring particles complete 42. And that steady, repeating pattern of tugs does something wonderful. Instead of letting the debris smear evenly around the circle, it herds the particles into pockets, corrals of gravity spaced along the ring, and holds them there. The arcs are flocks. Galatea is the dog, circling just inside the fence line, keeping the sheep bunched. The impossible clumps are simply what patience and resonance can build. The same 2 forces, we are about to see, that organize the entire outer solar system. Although, in keeping with everything else about this planet, the shepherd may be losing her flock. Observations since Voyager show the arcs changing. Liberté has faded and shifted decade over decade. Courage has wandered. Some models suggest the arcs are a temporary arrangement, dust from some geologically recent moonlet collision, still settling, still leaking away, and that we may be living, by cosmic luck, in the brief era when Neptune happens to have arcs at all. Check back in 10,000 years. The rings of Neptune may be a photograph of smoke. The small moons that share this region are rubble with orbits, and I mean that kindly. Remember, they are the reassembled wreckage of Triton's arrival. Proteus, the largest of them, is a dark, lumpy world of about 400 kilometers, roughly the largest a body can be while still refusing to be round. And gouged into its side is a crater called Pharos, more than 200 kilometers wide, a wound covering most of a hemisphere. Whatever hit Proteus came within a whisper of shattering it entirely. It may have done more than almost shatter it. In 2013, an astronomer combing through years of archived Hubble images found a speck nobody had ever noticed, a 14th moon of Neptune, later named Hippocamp, a tiny thing, about 35 kilometers across, orbiting suspiciously close to Proteus. The leading account of its origin: Hippocamp is a splinter, debris blasted off Proteus by the Pharos impact, coalesced into a moonlet of its own. A chip off the old block, still circling a few steps from the scar it came from. Neptune's satellite system, read closely, is a crime scene. The stolen giant on the outside, backwards, the reassembled rubble on the inside, the splinter beside the crater, and Nereid swinging wide and lopsided in the distance, still shaking, as it were, from events 4 billion years old. Now widen the view, beyond the rings, beyond the moons, because Neptune's true kingdom is bigger than anything in orbit around it. Beyond Neptune lies the Kuiper Belt, a vast, sparse ring of frozen worlds. Pluto is merely its most famous citizen, extending out to twice Neptune's distance and beyond. Billions of objects, comets in cold storage, the construction debris of the solar system. For decades after Pluto's discovery in 1930, it was a lonely oddity. Only in 1992 did astronomers find the second Kuiper Belt object and realize the outer solar system was crowded. And the shape of that crowd, who orbits where and how, turns out to be a signed confession. The signature is Neptune's. Here is the confession in one sentence. The outer solar system did not form where we find it. The giant planets were born closer together, closer to the sun, packed tight. And in the early ages, the leading models say, their mutual gravity rearranged them, and Neptune, the outermost, migrated outward, plowing slowly through the primordial disk of icy debris like a snowplow moving through gravel. A migrating giant does dramatic things to small worlds. Most of the debris in its path got scattered, flung inward, flung outward, ejected from the solar system entirely. Some of it, Neptune handed sunward for the other giants to hurl away. But a special fraction met a gentler fate. As Neptune crept outward, its gravitational rhythms swept ahead of it like the wake before a ship, and small worlds could be caught in those rhythms and carried along, pushed gently outward ahead of the advancing giant, locked in step. Pluto is the most famous passenger. Pluto orbits the Sun exactly 2 times for every 3 orbits Neptune makes. Exactly. 2 to 3, forever. This is not a coincidence of the current era. It is a lock, the same kind of resonant lock that Galatea keeps on the ring arcs, scaled up to planets. And it comes with a guarantee. Although Pluto's stretched orbit actually crosses inside Neptune's, for 20 years out of every 248, Pluto is nearer the Sun than Neptune is. The two can never collide. Never. The resonance choreographs them. Whenever Pluto makes its inward crossing, Neptune is always, necessarily, far away around its orbit. 2 dancers who share a stage and are never once in the same place. They have kept this arrangement for some 4 billion years, and they will keep it for billions more. And Pluto is not alone. Hundreds of known worlds share that same 2 to 3 lock. Astronomers call them Plutinos, little Plutos. An entire dynasty of small worlds, all pushed and gathered by the migrating Neptune, all still marching in its rhythm today. Other resonances hold other families further out. Mapping them is how we reconstructed the migration in the first place. The Kuiper Belt is Neptune's wake, frozen in place, the pattern of gravel that tells you exactly how the snowplow moved 4 billion years after it passed. And here I want to say a kind word to everyone who has never forgiven astronomy for what happened to Pluto. I know you are out there. You write to me. Consider this a small consolation. Whatever a committee decides to call Pluto, the solar system itself treats it as royalty. It holds the safest orbit a small world can have, personally guaranteed by a giant planet, escorted through every single lap it has made since before there was life on Earth. Pluto was never demoted in the only ledger that matters. It is a ward of Neptune, and Neptune does not forget its own. So let the full inventory of the kingdom settle for a moment. The last giant planet governs a retinue of 16 known moons, one of them a captured Pluto-sized world. A ghost ring system with impossible arcs, shepherded by resonance. And beyond that, an empire of ice stretching billions of kilometers, Pluto and its hundreds of resonant cousins, the whole architecture of the outer solar system, arranged, sorted, and escorted into place by Neptune's slow, ancient migration. The planet found with a pen turns out to be the landlord of the map's entire edge. Even the future of the kingdom is already written, and it is spectacular. Triton, remember, orbits backwards, and backwards, in a system of tides, means doomed. The tidal bulges Triton raises on Neptune act as a brake on the moon's contrary motion, and so, with exquisite slowness, Triton is spiraling inward. Not on any human timescale. The fall will take on the order of 3.5 billion years. But the ending is not in doubt. Triton will descend until it crosses the invisible line called the Roche limit, where Neptune's gravity pulls harder on the moon's near side than its own gravity can resist. And there, the great moon will be torn apart. Not an impact, an unraveling. A Pluto-sized world shredded into a torrent of ice and rock, spreading along its orbit into a disk. And in that moment, long after the sun has swollen and the Earth's story is done, Neptune will acquire a ring system to rival or exceed Saturn's. Massive, brilliant, wrapped around the blue giant like a crown, made from the body of the moon it stole. The theft, 4 billion years later, repaid as jewelry. If any eyes exist in the galaxy then, the 8th planet may briefly be the most beautiful thing this solar system has ever produced. One more widening of the lens, and then we will come home. Astronomers surveying other stars have made a census of the galaxy's planets, and the single most common kind of world out there, around star after star after star, appears to be a world between Earth's size and Neptune's. Sub-Neptunes, they are called. Our galaxy, it turns out, does not specialize in Earth's or in Jupiter's. It specializes in something closer to Neptune. The dim blue world at the edge of our map, visited once, for one night, may be the nearest example of the most ordinary kind of planet in the universe. When we finally learn to read Neptune fluently, we will be learning the galaxy's native language. Which makes the final fact of tonight's story stranger still. We have never gone back. No mission has returned. None is even on the calendar. Why not? What it would take, what almost happened, and what is left of the one machine that made the journey. That is our last chapter. So why has nobody gone back? 37 years. Every other giant planet has had its dedicated mission. Jupiter has had long-lived orbiters circling it, with more machines on the way. Saturn had Cassini for 13 glorious years. Even Pluto got its flyby. Neptune, a full-grown giant with the solar system's fastest winds, an ocean moon, a magnetic mystery, and the keys to the galaxy's most common kind of planet, has had one visitor, whose cameras were built in the age of the 8-track tape. This is not for lack of wanting. Scientists have proposed return missions for decades. The problem is arithmetic, and the arithmetic is brutal in 3 ways. The first is distance, which really means time. There is no straight road to Neptune. A spacecraft must either carry impossible amounts of fuel or borrow speed from other planets along the way, and the journey takes on the order of a dozen years, often more. The people who launch such a mission spend a major fraction of their careers waiting for it to arrive. A scientist who joins a Neptune mission at 40 may be emeritus at orbit insertion. The second is sunlight, or the lack of it. At 30 times the Earth's distance, solar panels are all but useless. A Neptune orbiter must run on nuclear batteries, powered by a special isotope of plutonium that is rare, expensive, and produced in only tiny quantities. For years after the Cold War, production had stopped entirely. It has restarted, slowly, but every gram is contested by every deep space mission on the books. The fuel for the lamp is scarcer than the will to light it. And the third is the calendar itself. The efficient routes to Neptune lean on a gravitational boost from Jupiter, and Jupiter is only in the right place for a stretch of a few years out of every 12. Miss the window, and the door closes for a planetary generation. None of this makes a mission impossible. It makes it a choice, a large, expensive, decade-spanning choice, competing against every other dream planetary science has. And in the most recent round of that competition, in 2022, the American planetary science community sat down, as it does once every 10 years, to rank its priorities for flagship missions. A grand Neptune orbiter concept was on the table, a mission called Neptune Odyssey, designed to circle the planet, study the rings and the magnetic field, and send a probe into that blue atmosphere at last. It came second. The community chose Uranus. I will not pretend that decision did not sting for the Neptune scientists, some of whom have now spent an entire career on a planet they saw up close exactly once, in their youth or before it. But I will also be fair. The reasoning was sound. Uranus is nearer, cheaper, reachable on better schedules, and every bit as unexplored. An answer from either ice giant illuminates both. If the Uranus mission flies on schedule, launching in the 2030s, arriving in the 2040s, then humanity's second dedicated ice giant explorer will report back roughly 60 years after its first. And Neptune? Realistically, the next spacecraft to see it up close will likely launch no earlier than the 2040s and arrive somewhere around mid-century, whether it comes from NASA, from Europe, or from China, whose scientists have sketched concepts of their own. Sometime around the 60th or 70th anniversary of that August night in 1989, perhaps, a new machine may finally slide into orbit around the blue giant, carrying instruments not yet designed, built by engineers not yet born. If you are young, you may see it. And I mean that literally. Somewhere tonight, possibly listening to a voice like this one, is a child who will be a propulsion engineer, or a magnetometer specialist, or a flight director on the mission that goes back to Neptune. The road between here and there runs through ordinary things. A library book, a cheap telescope, a video that would not let them sleep. Stranger careers have started from less. Meanwhile, the first visitor is still out there, and I owe you the end of its story. Voyager 2 never stopped. After Triton fell away behind it in August 1989, the spacecraft flew on, downward, southward, out of the plane of the planets, into territory no mission had ever mapped. In November 2018, 29 years after Neptune, it crossed the heliopause, the boundary where the sun's outflowing wind of particles finally stalls against the thin breath of the galaxy, and became only the second human object ever to enter interstellar space, still taking measurements, still reporting home. It is out there tonight, right now, as you listen, nearly 140 times farther from the sun than the Earth is, more than 20 billion kilometers away, so far that its radio whisper, traveling at the speed of light, takes the better part of a day to arrive. Its plutonium heartbeat weakens by a few watts every year. Its engineers, some of whom were not alive at Neptune, ration the remaining power instrument by instrument, shutting down one sense after another to keep the others listening a little longer. Sometime in the coming years, the mid-2030s perhaps, roughly half a century after launch, the last transmitter will fall below a whisper, and the longest conversation in human history will simply fade out, mid-sentence. The machine will not notice. It will keep going, silent, intact, carrying its golden record of greetings and music, outliving its makers, outliving perhaps everything its makers built. In about 40,000 years, it will drift closer to another star than to our own. The last close-up witness of Neptune, sailing on into the gallery of stars with the photographs, as it were, still in its coat pocket. I find I do not feel sad about that. A tool that outlasts every task it was given, still faithfully pointed outward. That is not a tragedy. That is the best ending any voyage has ever had. And so we come back around, as promised, to where we began. A crowded room in Pasadena, the night of August 24th, 1989, everyone watching 4-hour-old light. You know, now, everything that room was about to learn. Let it assemble one more time, gently, in the order we found it. A planet discovered by arithmetic, the only world found with a pen, waiting patiently in Galileo's notebook for 2 centuries, circling so slowly it has completed 1 single year since we learned its name. A 12-year road to reach it, traveled by a half-deaf machine with a jammed shoulder and 69 kilobytes of memory, arriving 1 second late after 7 billion kilometers. A world that should have been still, and was instead the windiest place the sun owns, twilight air outrunning sound, driven by a buried fire nobody has explained, its hurricanes only skin deep, its patience 4 billion years long. Storms that live and die like mayflies, clouds that vanished planet-wide while we watched, keeping time, of all things, with the heartbeat of the sun. Auroras hiding at the wrong latitudes, found after 35 years of looking. An interior with no floor. An ocean deeper than worlds, raining diamonds through the dark onto ice that is somehow also water, wrapped around a buried Earth-sized ember as hot as the face of the sun. A stolen moon that erupts at 40 degrees above absolute zero, keeps a hidden sea, perhaps tipped its captor sideways, and will one day come apart into the grandest ring system the solar system has ever worn. Rings named for the discoverers. Arcs named for liberty, equality, fraternity, and courage, held bunched by a shepherd the size of a small city's horizon. A splinter moon beside the crater it was born from, and beyond it all, an empire of ice arranged by Neptune's own ancient migration, with Pluto, safe forever, dancing 2 beats to Neptune's 3. All of that from 1 night of data, and 37 years of squinting at a dot. Imagine, I say this with real wonder, imagine what an orbiter would find. Because we know now, in a way the Voyager generation could not, exactly what to ask. An orbiter could hang above those storms season after season and finally watch one be born. It could trace the magnetic field through its 16-hour tumble and read, from the outside, the true anatomy of the electric ocean below. It could drop a probe into the twilight blue and taste the air on the way down, the experiment the Galileo mission ran at Jupiter a generation ago, never yet attempted on an ice giant. It could fly low over Triton, again and again, sniffing the geyser plumes for the chemistry of that hidden sea, the way Cassini flew through the fountains of Enceladus and changed the search for life forever. Every one of those measurements is within the reach of machines we already know how to build. Nothing is missing except the going. But that is for the engineers of mid-century, and for the children falling asleep tonight. Our journey is done. If you are still awake, thank you for keeping me company all this way. If someone beside you drifted off an hour ago, I consider that a compliment, not a defeat. Leave the story playing. Neptune has never once minded being watched by closed eyes. Out there, right now, at the edge of the park where the streetlights begin, the blue giant is turning through another 16-hour day. The wind that never stops is running its ancient laps. The arcs are holding, for now. Triton hangs fixed in its sky, glass ice quietly building pressure over the geysers, the long fall not yet begun. The sun, from there, is only the brightest star, and somewhere far beyond it, a small, silent, faithful machine is still sailing outward, carrying the only close-up memory of that world that humanity has ever made. One planet found with a pen. One machine that kept an appointment 12 years and 7 billion kilometers in the making. One night of pictures, 4 hours old before anyone saw them, still teaching us 37 years later. Space, slowly, for the hours you can't sleep. The park is quiet now. The grapefruit sun is down among the trees, and the rice grain at the edge of the grass turns gently in the dark, keeping its own long calendar, expecting no visitors, holding its rings and its stolen moon and its patient, ancient wind. It kept its secrets for 4.5 billion years and gave us one night's worth. The rest will keep. Some stories are better for being finished slowly, and this one has 100 more years of pages left, waiting for the readers who come after us. Rest easy. Sleep well. Good night.